Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over an example of how you can use the ICE chart to find the concentration of H3O plus, the hydronium ion, for a weak acid. So when you're given the molarity of the acid solution, you can then use the Ka value. You can use your ICE chart to find out what the equilibrium amounts are in terms of X, and then solve for X, and then see and then use that X value, which is going to be the same as the concentration of your H3O plus concentration. The other thing you want to keep in mind is this X is too small approximation. We'll be using that as well, and in another video I will show what to do when it doesn't work. Okay, so remember the 5% rule for checking the validity of the X is too small assumption or approximation. So here in this problem, when you're given a molarity of a certain acid, here we're using HCN. HCN is a weak acid. So they're giving us the molarity of that, and they want to know, okay, what's the concentration of H plus ions in this acid at that molarity? So the first thing you need to do is have a balanced equation. If they don't give you one, you have to figure it out yourself. And so remember, HCN is reacting with water, and so HCN is going to pass a hydrogen or an H plus ion, a proton, to water, which makes the hydronium ion, and results also in the CN or cyanide ion. So this is a balanced equation. Everything is in a 1-to-1 ratio. So let's begin. So at first, the concentration of the HCN, the initial HCN, is 0.100 molar. And we're not really going to consider the water. The water is ubiquitous, or there's a lot of water there, so we're not going to look at the change in that. So water is not really going to be involved in this. What's going to happen is we're going to have 0 molarity of water. There's a little bit of hydronium ion in the water because of the autoionization of water, but it's very, very small compared to the molarity of the acid and the Ka value of the acid. Okay, so this is approximately 0, and that's going to be 0 as well. Okay, so here's our initial conditions. Now we got to think about what the change is in terms of X. So obviously it's going to go in this direction. So we're going to lose some product and we're going to gain some reactant. Or I'm sorry, we're going to lose some reactant and gain some product. Sorry about that. So here, this is going to be negative. It's all 1-to-1, so it's all going to be, we're going to lose some X here, whatever that is. We're going to lose some amount X, but we're going to gain some amount X here, and we're going to gain some amount X here. And so when we put this together, our equilibrium concentrations are going to end up being 0.100 molar minus X, and this is just going to be plus X plus X. So then, now all we need to do is put these equilibrium expressions into our Ka expression. So Ka is going to be equal to, remember, products over reactants. So the concentration of H3O plus multiplied by the concentration of Cn minus all over the concentration of HCN, okay, at equilibrium. So this is going to be the same as, if we put the x's in, this is going to be x times x. Both of these are x, so that'll be x squared. And then we have the expression for the concentration of HCN, which is this here. So it'll be 0.100 minus x. And again, all right, this is going to be equal to the Ka value. So the Ka value for this is going to be 4.9 times 10 to the negative 10. So this is equal to 4.9 times 10 to the negative 10. So here's our expression. Now all we need to do is solve for x, and x will give us the concentration of the H3O plus ion, the hydronium ion. So here's where we can use the x is too small approximation. So, and it's a good bet that we can use this, because if we look at the Ka value and compare that to the initial concentration, it's a huge difference. So if you have 0.1 here, that's 1.00 times 10 to the negative 1. And here we have 10 to the negative 10. That's a difference in power of 9, right? So this is definitely going to this is a valid time where we can use the x is too small approximation. So then what we do is then we just say, well, x is too small. It's so small, it's negligible, that basically even if you subtract out x, it's still pretty much 0.100. So why not just get rid of it and say, okay, we'll have x squared over 0.100 is equal to 4.9 times 10 to the negative 10. So then all you do is you solve for x. You multiply both sides by 0.100, and then you take the square root of both sides, and then you get x, and then that x ends up being, let's see, so x then ends up being equal to, what is it, 7.0 times 10 to the negative 6. 7.0 times 10 to the negative 6 molar. Okay, so then what we can do is then we can use the 5% rule and see if that works out. So the way we do that is we then take our x value, right? We're going to take our x value and we're going to relate it to HCN and see if that follows the 5% rule. So what we do is basically we're going to take x, so x, which is 7.0 times 10 to the negative 6, and we're going to divide it by here, that's the whole. So what we start with is 0.100 multiplied by 100, and that basically gives us a really small number. So that's going to be 7.0 times 100. It's going to be 7.0 times 10 to the, let's see, I think, so 5? -3. So this will be -3%. So that's definitely less than 5%. So definitely validated. So then this will be our x value. And so then we can then find the concentration of the HCl. So of H3O plus, the hydronium ion, which is X. So basically this is the, that's the concentration of the hydronium ion for this weak acid. So I hope this was helpful. If we weren't asked for pH here, but if we wanted to define pH, then we'd take the negative log of that, and that would give us the pH for this weak acid. I hope you enjoyed this video. If you like this video, please like, share, subscribe, hit the notification bell. Thanks for joining me, and I'll see you next time.